Okay, so welcome everybody. Thanks a lot for being here, and thanks, Francesco. Again, let me first thank our sponsors. So the CNRS, the Fondation Mathématique Adamar, and the IHES, which is clearly, obviously, hosting these seminars. So thank you. And we are very, very happy to have Francesco Russo from the École Polytechnique telling us about conformal block decompositions for thermal CFTs. So please, the stage is completely yours.
Okay, thank you a lot to the organizers for having me. Yes, as Eduardo was saying, I will talk about this conformal block decomposition for thermal CFT. This is some work done, with Ilya Buric for Casimir and Alessandro Vichi. And okay, so let's start. And first of all, let's try to say why we're interested in computing conformal blocks, but even before, what should we be interested in, like, conformal field theories in general. So let's start by some basics. And like I would say that lots of people from many different backgrounds are in fact interested in conformal field theories because you can encounter them in very different frameworks. For instance, if you're just interested in QFT and you're flowing along the normalization group, it may happen that you find a fixed point and you might have there some conformal symmetry. And so you're talking about a conformal field theory in that case. Also, for some kind of instant transition hidden there might be a description of your physical transition by some conformal field theory. Or again, when you're talking about holography, the most famous example is that you have gravity in IHES, and this is due to some conformal field theory on the boundary. So from many different perspectives, people might be interested in conformal field theory in general. But also, I would say that conformal symmetry is important also for many non-perturbative approaches to quantum field theory in general. And the one I'm going to talk, let's say, a bit today, it's the conformal bootstrap, which is some non-perturbative approach to solve the space of conformal field theory. And the two main ingredients of this non-perturbative approach is something called crossing symmetry, which is some consistency conditions, and then there is actually this conformal block decomposition. So I would say that people like doing conformal field theory might be interested in performing this computation, this decomposition, because then this is an ingredient for the bootstrap. But okay, let's go back and let's go to CFTs in general, because first of all, I want to try to introduce all the tools that we will need in just standard and at zero temperature conformal field theory, and then we will see how this, how this will work, like more or less in a similar way at non-zero temperature. And also I want to stress that, okay, due to lack of time, I will not go into very details, but I think for mathematicians, this might be nice that this can be as rigorous as you want. So if you're interested in the topic and you want to understand things more formally, you can actually do that. Okay, so let's start by CFT. So we're working with a quantum field theory in some Euclidean space after the D, where these are our dimension, which is usually equal or greater than 3. At some point, we will fix it to be 3. And so as usual, we will have some Hilbert space of physical states, which we'll call H. And since we want our conformal symmetry, we want that this carries a representation of the conformal group. The conformal group is the usual map that everybody's familiar with. So it's a map that preserves angles. And this is locally isomorphic to S to the D plus 1, 1. Okay, and in this case, the Lie algebra will show the basis of the Lie algebra, which is the following. So P, D, K, and mu. Okay, so the mu and nu are the space-time indices, so going from 1 to D. And then, so P, space-time translations. D are the dilatations. M are space-time rotations. And then K are special conformal transformations. And you can see them as a combination of translation and inversion. Then we will mostly talk about fields and not a lot about states, and we can do this in CFT because we have this kind of correspondence, which is the operator set correspondence. So fields and states are more or less in one-to-one correspondence, and so we will talk mostly about fields, which for us are local operators, which transform according to some representation of our conformal group, and we'll be interested mostly in the operators which are called primary, which are something that work on K, act trivially on them. Okay, so then the thing that we'll be mostly interested in from this kind of introduction is that the primary operator is characterized by the finite dimensional representation of our dilatations and space-time rotations. So we will be able to label these kind of primary operators by this delta and L, where delta is the conformal weight of dilatation, which is called conformal dimension. It's the weight of the dilatation. Then L is what people usually call spin, which is of course the weight of the rotation, so of mu nu. Then we want to know how to act with conformal transformation on this primary operator, so of X, and we will construct this by saying that in the origin we want this operator to carry a representation of this delta and L, so of this dilatation and rotation, and then we want to act on them in the usual way with an element of our conformal group, which is by the adjoint action, which is the following. And then from doing just some commutation relations, you can get a representation of the conformal algebra, the differential operators, which is the following. So if somebody is familiar with QFT, P and mu, you may be familiar with both of them. So this is P just translation, this is the usual derivative. Also mu is the usual operator, but then you also have some dilatation and the special conformal transformation which take this form. Okay, so from these two slides, I would say that the most important thing to know is that we will be interested in these local operators, and we know how they transform, and we know like the representation that they have, which is this delta and L, and this is the way operators act on them. So once we know this, we can go on to the next step, which is correlation functions. So the physically interesting thing to see in a theory most of the times are correlation functions, which are these Gn, which are just primary operators acting on the vacuum, bracket with the vacuum. You can see this as a map, which goes from R to the D to this vector space, which is the tensor product of V1, Vn, where this V1, Vi are the representation spaces of this local operator, so I. So once we have this, okay, now I'm telling you that this Gn is just some tensor in this kind of vector space, but we can say more about this because we know that we have this kind of conformal symmetry, which is giving us an extra constraint. The way to phrase this conformal symmetry is to apply this conformal symmetry is through these word identities. So we just put any conformal generator inside of this correlation function, then we know that the vacuum is invariant under conformal generators, and so we will have some kind of these xi are the generators that we were the differential representation that we were talking before. It's going to be clear, but like with this line, what I want to tell you that Gn is not just a random tensor in this vector space, but it's the invariant vector under this conformal group inside this vector space. Let me just be more precise with this example. So if we just do the easiest case, so the one-point function, you see that if you have translation, you act on this thing. It means that just you're doing the derivative over this G1, which is just a function of X because we have just one operator. And we're saying that since this word identity, we have this left-hand side must be 0, we have that this object must be 0, which is telling you that that thing, G1 of X, must be a constant from the first line. Then what we do, okay, but this is just one of the generators, our conformal symmetry. We also did the action of the dilatation, which is this D. We have some other differential equation. If we solve it, we see that not only this is constant, but this must be this one-point function is 0 if the operator has a non-vanishing conformal weight. So you see that conformal symmetry is actually very powerful to see what is the invariant vector inside this vector space. And for instance, for one-point function, you know that this is just exactly 0, of course, for operator with non-vanishing delta. You can play a similar game. Of course, it's a bit more complicated because now you have to use all the conformal generators, I guess, as a constraint, but this is just solving a differential equations, some of differential equations. For the two-point function, the same way, you see that this is completely fixed, and this takes this form, okay? And also for the three-point function, it's completely fixed, if not for an extra coefficient, which is this lambda, which is called the OP coefficient, and it's going to be important for later. And then let's go on. And then the next step is to talk about blocks decomposition, because if you try to apply the same machinery to 4-point functions, so to correlation functions with 4 primary fields, you see that conformal symmetry is not enough. So you have, again, your differential equations, but this is not enough to constrain univocally the form of it. But you see that this is going to be just some function of some conformal invariants. So you have some variables which are conformal invariants, and this G4 depends on some function of them. Okay, so now the point is to repackage this information in a useful way. So this fact that you still have this conformal symmetry and how you want to make it explicit in a sense. And the way to do this is by this block decomposition. The way we define that is by a projection. So we want to project on the space of primaries with this operator pi. And we just insert this identity inside the 4-point function. Okay, you have some prefactor which you can just ignore because it's some covariant properties under the conformal group, but let's focus on this sum. Okay, so now you have this kind of these are just coefficients which turn out to be related to the OP coefficients of the 3-point function, but then you have this function here, gi, which are what we call conformal blocks. And Z and Z bar are just what I was calling conformal invariants before. And so you see that this is like an optimal way to decompose your 4-point function, because you're completely, in a sense, separating the kinematics from the dynamics, which means that all the knowledge from the conformal symmetries that's just sitting here in this function, and then you have just some coefficients which are going to be theory dependent. So I mean, if you want to specify your theory, then you have to put some numbers. But otherwise, if we're just talking about conformal symmetry, all the information is sitting inside this GI. And of course, if you specify your theory, you need also to specify on which primaries you're talking about. But okay, so this is pretty nice because of this kind of, all the information about conformal symmetry is going there in this 4-point function. But how to actually explicitly write down these conformal blocks? How do you write them down? And there are different ways to do that. And one of the most efficient way, it's the one as by seeing these conformal blocks as solution of differential equations. And the way you do this, and it's okay. Now let's consider the quadratic Casimir of the conformal algebra, which is this C2. And let's insert this conformal Casimir here inside the block. So that's C2 inside. And now you see that if you want to act on the left with this operator C2, you will get something like this XXGI. And this X is just, again, X, I mean, the conformal generator, an element of the conformal algebra. And yeah, this is just a differential operator as the one we were seeing before. So that's just a differential operator acting on our block. But if we act with the same, so we go back to the first line and we act now on the right instead of the left, you see that this is just some irreducible representation of your of your representation of the rotation, of dilatation and rotations. And so you know precisely what is the eigenvalue for the conformal group in that case. So it's just some numbers. And so putting them together, you will get some non-trivial differential equations, which is the following: the quadratic differential equations, where these x are I mean, just to take a look at before, these are, I mean, a combination of these things. So it's just some non-differential operators in the space-time variables. And on the right, you will just have some eigenvalue problem. Okay, so now what do you do with this? Because you still have, as I was telling you before, this block is going to be a function of just the conformal invariants, what I was calling before Z and Z bar. But now this differential equation is going to be depending on all space-time variables. So let's say that we have 4 variables because we have, and we're in the dimension. So we're going to have some 4 times dimension differential equation. That's very complicated, of course. So you should find a way to make it better to get some information from it. And actually, you see that these differential operators preserve the functional form of your blocks. So this means that you can reduce the differential equation to one in just 2 variables, this conformal invariant Z and Z bar. And so you will end up that this operator on the left will just be something like this, where this D is just some hypergeometric differential equation. And so you see that it's much better because starting from a 4 times dimension differential equation to just a differential equation to variable, the story is much better, and maybe it's manageable. And in fact, it is. So for instance, in even dimension, in 2 and 4, something like that, you can get an analytic solution for these blocks. And this is the form, but the problem is that when you go to odd dimensions, you cannot do it anymore. And so you have to do other techniques. And one of these may be some series expansions, some solution from a series expansion. This means that you start from an ansatz. So this is the following. So you're going to have some expansion in your conformal invariant z at z bar times some coefficient, which I call this a of nj. And what you want to see is what are these coefficients in the series expansion. And the way you do that is that you act with the Casimir, and you want to impose that this is a solution of your differential equation. And so in this way, you can compute these coefficients. But this is even better because just the action of the Casimir is going to give you some close algebraic relation on the coefficient, so you don't have to act every single time with a differential equation, but you just need to solve some linear system of equations to get these coefficients. And this is pretty fast, and that's very efficient, and that's one of the ways you can get some expansion, some series expansion solution of your differential equation. Okay, but now when I was talking about this, I was adding some complications because I was talking about scalars mostly. When I say scalars, I mean some trivial representations under the rotation group. Of course, this is not always the case because we want spinning objects usually also. And if you want spinning object, all the form of this correlation function is going to be a bit more difficult because, of course, the space that we were talking before, this invariant tensor in this space is going to be a bit more complicated because the static structure is richer. You can do anyway the same game, a similar game. Okay, here we will skip lots of details. Just to show you, first of all, one detail is that we will encode all the representation and the rotation in this kind of extra label Z1 and Z2. So instead of putting indices and working with matrices, we will just work with some polynomial, with some extra polarization vector to encode all the information. And yes, you see that you have a similar form as before, but then you have an extra piece to deal with the transformation rule under this SOD symmetry. And you can play a similar game. So again, you have the 2-point function, the 1-point function is 0. The 2-point function is fixed, even though it's a bit more difficult. The same for the 3-point function. It's even a bit more complicated, but it's again fixed apart from some coefficients. And then you can do the same game also for the 4-point function, where you have some kind of conformal block decomposition. But now it's a bit more difficult because you see, okay, this was our expansion with respect to, this was our projection to the space of primaries, but then you see that we have an extra sum because in this case we don't have just one function for each primary, but we have more than a non-trivial function of your conformal invariance, and so that's why you have also these extra indices you're summing over this A and B, which are taking into consideration the non-trivial representation of the rotation of these O1 to O4. Okay, and at this point the questions are two. So first of all, how do we compute again this more complicated object, this GI of AB? Do we have again some Casimir differential equation? And we want this differential equation to have two properties actually as before. So the first one is that we want this to write in general. So we want to put the dependence over the external representation on trivial spin of these operators in some universal way in this differential equation. And the second thing that we want is that, okay, this is again will be some differential equation of tons of variables. We would like that we can reduce to some subset of variables again, as we were doing for the scalar case. And this is the case, and this is true. Both questions are, both the claims are true. So we can write a Casimir differential equation, which has got some universal dependence over the spin of the external representation, and also we are able to reduce, this differential equation to a smaller number of variables. This is a highly non-trivial fact, and I will just comment next slides. Just to give you an example, if you will have here two scalars and two spinning operators. So before, for scalars, you had two variables. Now, for this more complicated case, you can again reduce it. You will end up with 5 variables, but still, it's a bit better than before. Okay, so now let's say something why you have this reduction of this differential operator, and the reason it's coming from a tool from harmonic analysis, which are these spherical functions. So spherical functions are defined over a pair of groups G and K, where K is a subgroup of G, and they have some covariance property under the action of K. This is the function which are called spherical functions, which are this F. Then we're interested in this kind of definitions because it turns out that conformal blocks are spherical functions over our pair of group. In this case, it's going to be the conformal group, so this SOD plus 1, 1, and then as the subgroup is this kind of dilatation, so SO1, 1 times rotation, which are SOD. So once you know this, okay, first of all, like the first thing to check once you call conformal block spherical functions, that you check if the spherical functions were known for this pair of group. Unfortunately, they're not, so you need to compute it yourself anyway. But this is telling you anyway something nice, something interesting, and this is coming through this Harris-Chandra component map, which is a theorem, which is telling you that the Casimir operator acting on a spherical function f, and you can reduce it to a subgroup, which is the one that I call A of P. This is equivalent to reduce the differential equation on your Casimir differential equation, this subgroup A, and then act on your function. So in a sense, this is telling you that if you have a spherical function, like you can do this reduction without any problem, because this is a theorem, so it works. So you can just take your differential. So it's going to be like something that's going to happen always for the conformal blocks, so that you can always kind of reduce your variables to a subset of them, which are these, what I called before, the conformal invariants. Okay, and so now we have most of the tools, and we can start talking about thermal CFTs. But before, I don't know if you have any questions, because as usual, I'm going pretty fast, so we can just stop, yeah, for a minute. Okay, if not, okay. Okay, so now we have more or less the knowledge. So now you hopefully you know what is a conformal block decomposition at 0 temperature, and you know like the way that we label operators. So the first one is exactly the same. So we're labeling operators in the same way. The only difference now in non-zero temperature, like what I mean for non-zero temperature, is that you're going to take different correlation functions. So instead of the thing that we had before, now for correlation function, I mean this object here, where I put this beta mu to tell you that this is a different object. So for beta, this is the inverse of the temperature, and this mu are something that I would call chemical potentials. And okay, so I define a correlation function on zero temperature as a trace over your inverse space of states of your operators of phi of x, and you also add the insertion of these extra operators. So the first one is e to the minus beta d. So this is beta again is the temperature, and d is the dilatation operator. And then you have the extra one, so the e to the chemical potential times hi, where hi is a Cartan generators of rotation. So you're just putting some rotations there. Okay, in the line I just explicitly wrote down the trace. And okay, you can see already, I would just call sometimes this term e to the minus beta as q and y as e to the minus mu I. The point is that you can see already that the conformal invariants, the thing that we were doing before, so the word identities that we had before, they will not work in the same way in this case also, because you see that not everything, like if you put your conformal generator there, now they're not going to commute trivially with the things that you're inserting. So with this e to the beta d and the other rotation. So you're going to have, like, you can say that conformal invariant is a bit broken for these correlation functions, but you still have something, like you still have some subset of generators which you can use, and the subset is actually the one that are appearing there. So this the dilatation and the Cartan generators of rotations, because of course they trivially commute with what I'm putting there, because yeah, D commutes with the rotations, and yeah, so that's fine. So what can you do is that you can try to do this exactly what we were doing before. So the way we were constraining before, the 1-point function, 2-point function, you can try to do the same, but now with less differential equation, because you just have these two of them. Okay, and what you find out is that already the 1-point function, it's a non-trivial, it's generally non-zero. So I remind you that before this was trivially zero for all operators apart the one with zero conformal dimension. Now this is going to be non-zero. And also, I mean, you have the same, you can say that this 1-point function, we can put in analogy with the 4-point function, because now it's going to be some non-trivial function of some invariants, which are constructed again from the dilatation and the Cartan generator of rotations. So for instance, in dimension 3, these are my invariants, what I call like P and Z. Yeah, I'm sorry, I noticed this morning Z is the same as there, but these are different. I'm sorry for the use of notation. And so what you want to do is that you want to do the same as before. So as I was saying that before, the 4-point function was written as a non-trivial function of the cross ratios. This is again the case. So the 1-point function, non-zero temperature, you can write as a non-trivial function, which is this f that I called here, of my cross ratios, which are, okay, temperature, chemical potential, but this kind of invariance, this P and Z. And so now the question is, first of all, we can do the same game. So we can try to project the space of primaries, and we can see if there is a block decomposition now for this story. And there is, okay, so let's just see here. So we can define in exactly a similar way a block, in this case, by projecting this operator. Again, it's the same, this projection operator to the space of primaries, and you get some kind of block. Okay, so again, you have a very abstract definition of block, but then you want to know explicitly this function. One way to do this is that you can relate this function to the 3-point functions at zero temperature. And this is done by some kind of integral. This is very complicated. And this is definitely, this is not doable most of the times. And so the way that we want to do that is, again, to find a differential equation such that this block is a solution of this differential equation. And we'll use, again, the same strategy. So we will put the Casimir inside here, this definition. We will manipulate doing just computation relations and use the cyclicity of the trace. And we will end up, again, with a similar differential equation. What is nice, again, is that we can use also the same machinery as before, because we have, again, the identification of blocks as spherical functions. Okay, now the group is even more complicated. So the group now is going to be the conformal group times the conformal group, comma, the conformal group. This is because you have the trace, and so you have more copies of your conformal group sitting inside. And again, this was not known in the representation theory, I mean, literature of these spherical functions, unfortunately, so we have to compute by ourselves. But this is telling in a sense that we have, again, the nice properties of reduction in a subspace, and that we can, so we are actually working with less variables than it seems.
Sure, I understand.
Yeah. Okay, the one you can do a block decomposition, and this one you can actually do the same definition as before. So you just put a projection to the space of primaries, and this will define a conformal block, which is just this one. And then you want to do the same. I mean, how do you compute this block? And you want to see that this is a solution of some differential equation. And so you do the same step as before. So I will put here inside this trace, I will put the Casimir, and then I will just manipulate. So I will act on the left first and then on the right, and this will give me some non-trivial differential equation. The same step as we can do that in for.
I mean, why is the product of two SOP plus one?
Oh, this one, the spherical function is like that. You see what kind of spherical function it is? Yeah, I don't know. It's some non-trivial computation that you can see that. I don't know. I don't have an intuitive way of seeing that. I think you can. Yeah, you can like say that since you don't have just a single operator transforming under the conformal group, but you also have the trace. So you also have this kind of. You have also these extra operators. These extra operators. So when you're doing, I mean, when you're trying to identify with a spherical function, you see that it's just more complicated. This is non-compact, which means that it's worse than the previous case. But yeah, I mean, yes.
Francesco, the vacuum is still invariant under the SOD
Yes.
1.1
Yeah.
because just because some boundary condition in the thermal circle.
Yeah, I would say so. I mean, we're not that. I mean, what we're doing is really defining everything the same, like operators and states. They're defining it exactly in the same way. The only thing that we change, at least in this with this construction, is the correlation, the definition of the correlation function. So we just put the trace there, and so there we have some general operators. So I mean, in a sense, we're not. I know we're not wondering a lot about the vacuum because it's not only that which is appearing. We have just a sum over all our Hilbert space. So that's why that's the only thing which is different from zero temperature CFT. This is our case. Then, of course, sometimes when you talk about thermal conformal field theories, you mean something else, I would say. What people usually mean is the infinite temperature limit. So when you take the infinite temperature limit, then you have something different. And yeah, which is not what I'm talking about.
You have some breaking of translations.
Yes. In that case, you have some breaking of translation, but you're recovering something else. So I mean, also word identities are different. So that it's a different framework with respect to this one.
Sorry.
Yes.
What's wrong with the first formula? It's very complicated. But,
Yeah, the integral. I don't know. We don't know how to do the integral, I would say, because I mean this object is some kind of, yeah, this is just a three-point function with some extra variables, and you know how to do that in some very easy case, like if you have scalars only scalars, and if you switch off the chemical potential Y, you have some. You can do that. Mostly, you can do that from an IHES perspective. Okay, I don't know so many details, but that you can do. But otherwise, if you turn on all the variables, I mean, you can write it down explicitly. You have your integral, you can do everything, but then you just don't know how to do that. I mean, I don't know, but yeah. That's it. But the nice thing from this point of view, I think, is that it will connect three-point functions to your blocks. So you can see some equivalence where the blocks can be written as a OP coefficient times something else. So this is the nice feature of this way of writing stuff. Yeah.
But this integral is hard to compute, but everything is well defined. It's convergence. Or not?
Yeah, I would say so. I mean, this integral is just the shadow transform. I mean, you just do the shadow transform of this operator. So you do I mean, when you do the trace, you use the state operator correspondence to just write instead of n. Let me go back here. Instead of putting n and n, this one you can write as a shadow transform of the shadow of n and n on the other part. So this is everything is well defined. I would say that everything is convergent, and so principle you should be able to do that. Probably we didn't spend enough time to do that, but. Okay, so the way we're doing it was again by writing down some Casimir differential equation. And okay, so for the easier case, so we're fixing the dimension because in higher dimension you will have more variable, it's going to be more complicated. So we just did everything in 3D. So in 3D, just to take a look, this is the differential equation that we will end up with. This is in the case of scalars, only scalars operators, and so you have just three variables, and this is some quadratic differential equation in Q and Y, and you see those in the other variables. Again, this is too complicated to solve it analytically. I mean, if we switch off some of the variables, we can get some control over this, but in general, this is, for us, it was undoable. So again, the way we're solving it is by putting some scalar ansatz, which is the following, and then acting with the differential equation to get our coefficients. Okay, the thing that we can see, if you turn on the spinning representations, you're going to have an even more difficult differential equation, but still it's manageable because, again, the Harris-Chandra reduction is telling you that you can reduce to this space of 4 variables and that's it, and everything is nicer in this framework, and you just have your differential equation. Again, you can try to do that with the spinning ansatz. So you have, again, your kind of ansatz with your variables, and then you want to see your coefficients. In the same way you were doing with blocks, you can write some closed form algebraic system of equation for these coefficients, and so this is going to give you like some recursion relations for the function. This is pretty efficient, and we can solve it. Okay, this is just an example for some fixed local operator of an example of a block written in the series expansion. Okay, but now you may wonder why. 10 minutes? Okay. Okay, I don't need more. Okay. Okay, so now you can say why. I mean, everything was nice, I think, at this point, hopefully, but everything was also pretty abstract. And how can we check this? I mean, how can we sure that we did everything in the correct way? And the easy way to do that is to do some non-trivial check. And our non-trivial check will be free theory. So you want to see with some explicit theory, you want to construct some one-point function and then see that this one-point function will decompose into these conformal blocks to see that we get the correct result. So free theory, okay, so we will consider the scalar field theory of the fundamental field phi on the cylinder. And okay, this is the action, but we will not need it. We're just going to write in the usual way. So from canonical quantization, we have some kind of expansion in modes. So this is our fundamental field. A and A dagger are creation and annihilation operator, and Y are the spherical harmonics as usual. And from these, okay, so first of all, notice that the one-point function of phi, of course, it's trivially 0, because you have just one either annihilation or creation operator. So if you put inside the trace, this is just 0. So the first non-trivial operator for the one-point function is going to be phi squared. But for phi squared, we don't have an expansion in modes. So like our strategy was, first of all, let's compute the two-point function, this one, and then we will get to the one-point function. So the way we do that is just, we write down explicitly the two-point function as the trace of everything, then we do an expansion in modes, and then the only two non-trivial things are the two infinite sums with A and a dagger and A dagger A. You can do that, but just by using computational relations and cyclicity of the trace, and you can just see that this is this explicit form. So then you just plug inside the two-point function, and you can write this as a series, some series expansion of your variables. Okay, here we're partially fixing the frame, so that's why we're just two variables, so this radius and this theta. Okay, at this point, how to extract information from the two-point function to the one-point function, and the way it's an usual tool in CFT, which is this operator product expansion, known also as OPE. And the claim is that if you have two operators, you can write this as an asymptotic convergent series of these primary operators of mu times some prefactor, which is just some differential operator, completely fixed by conformal symmetry. So this is some tool used in standard CFT, and this is a convergent expansion. So this is pretty well known, pretty well under control, and also this complicated prefactor, which is this C. It's just some differential equation fixed by conformal symmetry, which is the following. So what you want to do? Okay, so I want to see that by expanding these things in my coordinate r, so fusing the two operators, I should get some expansion in one-point function, which is what like the OP is telling me. And the leading one-point function which I can extract is this phi squared, so the one that we were after. And okay, you see, this is just the first expansion in R of this equation. This is going to give me this kind of solution. Of course, you can go on with the expansion. So you can go to the subleading terms, and the subleading terms are going to give you, first of all, the stress tensor. And then the next one, we're going to give you all the higher conserves currents, higher spin currents. And in a similar way, you can start from a 4-point function of the fundamental fields phi. Again, this is just, as in the previous case, it's just more complicated with the A and the dagger. You need to do the computational relations, but you can do that. And once you get that, you can perform the OP and get other 1-point functions. So generally, you can just repeat this scheme and you can get as many 1-point functions as you want. Okay, so this was just some easy computation in free theory. And at this point, we want to test our conformal blocks. So the claim is that this function should have a non-trivial decomposition in our blocks, if the story is true. And of course, you see that if there is a decomposition, it's highly non-trivial because, I mean, the object, it's a 4-dimensional it's a function of 4 variables, so that the fact that you have a decomposition, it's not just by random. And you can have it, so you can just write explicitly the 1-point function in the previous way. You can compute our blocks, and you see that you have some kind of a precise expansion in blocks of your 4-point function, of your 1-point function. And the other nice feature is that the number which is sitting next to the block, so this kind of 2, 3, 6, 4, 7, it's also something interesting in conformal field theories. These are the OP coefficients, which we were talking before, because, I mean, here you always have some kind of OP coefficients. And so in performing this decomposition, you also get some kind of information about the OP coefficients in free theory. Of course, you can say, okay, that's free theory. OP coefficients are coming from 3-point functions, so you should be able always to compute them. That's true, but this is much more efficient, this decomposition, rather than computing them all. So for instance, we were computing like these OP coefficients just by doing this decomposition of about around 10 million of operators and up to spin 28. So we were also wondering if through this decomposition, we could get some interesting properties of these OP coefficients at high delta. And okay, these are just some of the plots. So this is our extracted OP coefficient for scalars divided by the multiplicity. And you see that we don't know what to expect. This is just some exploration, that after some point, they seem to converge to some kind of curve. And this is also the same for the spinning OP coefficients. So OP coefficients where 2 of the operators have some spinning representation. And of course, here you will have, as I was saying, more than 1 block. So that's why you have different colors, because different colors would be different blocks, different tensor structures. But you see that in our basis, a suitable basis of these tensor structures, only one is dominating and the other one is going to 0. And yeah, so we don't know, but hopefully maybe one can extract some information about the high delta limit of these OP coefficients. Okay, so but like as a check, this one was working perfectly, and we check at a like high order in Q that you have an expansion, and this is correct. And okay, so let me just conclude. Let me first sum up what some of our results. So we were able to write a Casimir differential equation for this kind of 1-point functions. And also in general, we connected these also thermal correlators to the spherical functions language, which I would say is also useful for just the general framework. Then we were able to solve it again by some recursion relations with expansion in Q. And so we were able to get these thermal blocks explicitly for 1-point function. Then as a future step, okay, the first thing one can do, okay, you did it for free theory, can you do also for other maybe non-trivial theories? And what can you can get some plots like the OP coefficients, can you use them to get something physically interesting? And so one may do the decomposition of generalized free field or some interacting theory for holography. Or another point of view was another possible future plans might be to study the high temperature limit of blocks. So we have a differential equation, and what we're doing now is we're just solving for the small temperature limit. So like near T almost 0, T close to 0. And can we say something else about these blocks, like this behavior at T going to infinity? Can we say something more? It's just we have a differential equation. We just need to study that. It's complicated, but maybe we can say something else. And then another question, maybe a more complicated question, is to be, we can also repeat the same story for higher points. So we just did it for the 1-point function because this is the first non-trivial object where you can do the decomposition into blocks. But all the machinery will just apply also to the 2-point function, 3-point function, and so on. And the point is that there is something physically interesting there, because do you have some kind of consistency conditions or crossing equations on the 2-point functions? Can you find some kind of positivity to do some bootstrap machinery? And okay, so these are open questions. I hope that everything was clear, at least something, and thank you for your attention.
Thank you. So let me start immediately with a question which I have, if I can. Well, we have plenty of time for questions, but Just wanted to ask you, so is there any consistency condition on the one-point function crossing like, I don't know, like this KMS, I don't remember, like,
Yeah,
Is it-
KMS is for two-point function.
it's for, so you don't have like, for example, some condition that is related to the periodicity along the terminal zero.
Yeah, I don't know of any. That's why I'm talking about going to higher point functions, because yeah, for the one-point function, I mean, at least I don't know of any kind of consistency conditions. Because we're also not doing any OP in a sense, so.
In one plus one D, there is, right? If you consider like instead of the thermal circle times a line that
Mhm.
times a circle,
Mhm.
then you can, there's like a modular, like that's cross equation that you can use. There's actually a crossing equation for torus.
Yeah, yeah,
point functions.
yeah.
But I think.
Yeah, I think in this
just on
case,
the plane,
because you have S2 times S1 in this case, so I don't know if you have any things like that, yeah. Yeah, this would be something that we would be after, because if we can find some consistency condition, we can just try to apply the same machinery, yeah.
For example, in principle, you can swap the two S1 and S2 now, because I mean, it was if you started with an homogeneous CFT, I mean, it is, seems like an arbitrary choice to just choose one thermal circle than another. Or not, perhaps I'm just saying something totally.
Yeah, and we haven't thought so much about this. I mean, it was nothing obvious, at least that, or that it was known before, I think, because we looked for that. We saw the case of 2D where they were doing different things, but I think since we have a different geometry, I don't know if it was just, just translating the same analogy in that case. So yeah, I mean, we can talk about this. I mean, I really don't have an answer for now. I mean, the easiest case is the KMS, which is known, which is famous for the two-point function, and that, of course, is going to be applied in this case. But for the one-point function, I don't know, also because most of the times people are working with this high temperature limit where the one-point function is fixed. So you don't have this block decomposition in the high temperature limit, but you just have a fixed function. So you cannot have any kind of freedom in this high temperature limit. And so people were just interested in higher point functions. So
that was the case of the famous paper by Samuel Duffy, for example.
Yeah,
They
yeah.
were working the
yeah, they were working the paper by 2017-18. They were working the temperature limit. Yeah, and also most of the paper about that time, I think they were doing this. I think also because it's more probably physically interesting. Also, Junchen, that's what he does. It's more physically interesting probably to extract. There you have just a coefficient, and this is something that you has a physical meaning. In this case, instead of having this kind of extra coefficient, you just have OP coefficients, which is something that is, yeah, just different.
Also, how do I see the convergence issue for the OP expansion with this?
No, here I'm not doing any OP. Here I'm just doing OP in free theory. But
I mean,
for the block decomposition, I'm not doing anything.
basically, why can't you just take T go to infinity? What's happening to the convergence of your block expansion or
No,
the one conformal?
yeah, the differential equation is gonna, yeah, it's got some kind of, you cannot do that. I mean, wait, let me see. Let me just phrase it. Okay, so you have an expansion which is at very only a small temperature. So it's a polynomial in the temperature, let's say. So it's just meaningless to do the expansion just on the solutions, but the level of differential equations also you cannot do that. You cannot easily just do the T to infinity and having something meaningful. You have to do something smarter and just, yeah, I don't know.
But we know there shouldn't be a cut some when you take T go to.
For the blocks, you mean, for the
Yeah,
solutions? And from the solution point of view, I don't know, because I'm doing some serious expansion and it's going to be convergent when T is small, and I don't know what's going to happen in other regimes. So then I'm able to resum some of this function, and I have some 3F2, so maybe, yes, you will have some kind of cut at some point.
So you have been able to resum the block.
Yeah, the block for some specific values.
Nice.
And you have some 3F2, so you have some cuts probably because of the analytic region of the either geometric. But okay.
But that cut has to somehow disappear when you resum all the expansion. Because your one point function is like well defined, smooth as you take the decomposition. There should be some constraints there.
Okay, yeah, probably, yeah.
It's some kind of locality, like.
What uses recently this thermal here?
What, sorry?
Also, David.
Oh, yeah, they're using a lot this thermally effective field theory to get things from this. Yeah, that's true. They're also working with this geometry in that case. So this SD minus 1 times SD, and they're getting things by doing these EFT computations. Yeah, I would say, yeah, we were comparing some of our results, like mostly we were using particular function, we were comparing them, and they're able to do this kind of limit. Yeah, we want to see if we are able to get also the same information, but from a different perspective, which is these blocks. Yeah, I don't know if it's maybe for something it's better than the EFT, for something not, I don't know. Yeah, so that's the point. Also because most of the times their computation, I think it's going to be some saddle point, solving some saddle point integral. So maybe this might be nicer and cleaner way to see some of the results.
Okay. I was a bit confused about this comparison with the I thought the difference was mainly that you have this Y, this chemical potential stuff.
Yes. So yeah, the difference are two. So yeah, first of all, there is this what I call this chemical potential. I don't know if it's standard terminology, probably not. Is that this is a chemical potential for rotations, and in fact, we do need this. We saw because otherwise, without turning on this chemical potential, we cannot write a Casimir differential equation. So it's like for blocks. When you write conformal blocks for 4-point function, and then you want to fix some of the cross ratios, you see that you cannot just do that you cannot just do that because sometimes the quadratic Casimir will not exist. Like if you want to do for z equals to z bar, you cannot just do that, but you will use also the quartic Casimir if you want to find a solution. And in the same way, if you want to turn it off, you can probably be able to do that, but then you will also need the quartic Casimir in this case. So I think the intuition is that if you want to write a differential equation, you need this extra chemical potential. And then the extra difference with the paper by IHES et al. Was that when you have when you're going to the t going to infinity, you're recovering some of the other. Okay, first of all, you don't have the chemical potential, but then you can have some expansion in t because t is the dominant part, and so this is fixing completely the 1-point function apart from a coefficient. So I mean, for them, this is
them doing t to infinity.
No, I would say that's it, because that's the different geometry that they're calling this RD minus 1 times S1. This would be our geometry.
For me, the infinity is the thermal radius.
Yeah, it's like, but it's like extracting just it's like doing our S2, and you see that this S2, it's going to be just the flat space, and this is the case if the thermal circle, I mean the temperature is like much bigger than the other variables, and so that you have this thermal circle, the variable in the thermal circle dominating for all the other variables. And so that's why the dominant part, that's why I call it high temperature limit, because the dominant part, you're going to just see the temperature and you're going to see the other things. And so you can just have this fixed 1-point function times a coefficient. And also there, I mean, because in that case, you don't know, I think, how to do subleading corrections with respect to the temperature, because that's when you say temperature is much bigger than everything else. And then to do subleading corrections, you need to do this EFT story that David and others are doing now. So to actually work with this geometry, and this is allowing you to do subleading corrections with respect to the temperature. This limit I don't understand precisely how to do that for now. I mean, there is some abstract way of writing that. I don't know how to do that from our point of view, and that's non-trivial, but I think this would be
from 2-point function of an expansion.
Yes. Oh yes, we in free theory, you mean yes. Yeah, if you do this,
take y equals 0.
Yes, you still cannot. Okay, you can resum in some case. Yeah, you can resum in some case this, and you can do the temperature limit if you, as you're saying, you switch off y. You can do that, and you match with the leading term, then you expand in T at IT, and you see that the first term is going to match with what they're talking. So you can actually see this. So let me just say that better. So you have these, you switch off chemical potential because otherwise you don't know how to resum. And then you will have some kind of closed formula for this 2-point function. Then you expand in the high temperature limit and you take the first contribution. And this first contribution is going to be equal to what they're talking about. And this we checked also for the 1-point function. We were able to, if we do some kind of manipulation, we were able to actually extract the coefficients in the high temperature limit. And this again matches with, of course, what they have, because that should be the correct thing. But of course, in general, we don't know how to do that. If we just see the differential equation of our solution, we generally don't know. That's something we're working on now, because yeah, it would be interesting. Yeah.
If you could solve things, you would have the blocks on SD-1 times S1.
Yes. I mean, that's our blocks, but we have in this small temperature limit. So it would be nice to also do this, and yeah. I don't know what it is. I have no idea.
Okay, so any other question?
Ask a question from online.
Yep. Can you hear me?
Yes.
Okay.
So you have here one Casimir, right, for 4 variables. Do you
Yeah.
expect that there are more Casimirs hidden that would commute with this one as well?
Like the quartic Casimir and so on, I would say yes. That if
So
this
how much? How many? Like, do you get like the maximal number? Like, do you get 4 of them, you think, or?
Okay, I don't know many. Yeah, we didn't investigate on that. I would say that you can get other, like the quartic Casimir, and this would be the case that you need if you fix some variables. But yeah, we haven't tried to compute them or see how many of them. So yeah, I don't know. Like the question is probably yes, but I don't know.
Any other question? Okay. Oh, well, thanks a lot, Francesco.
Thank you.
And we are back in, I remember, 30 minutes. 30 minutes, okay.